Yeah, good morning. And now we'll start with an SEN class where we have stopped. In last class, we are discussing on how the evaluation process of the resource allocation will be done. So, how the different criteria issues in resource allocations are taken into the consideration, and we have seen how the power whatever is there will be based on throughput by delay, and throughput and delay will be always inverse to each other. That is, if throughput is very good and more, and automatically the delay will be reduced. If delay is more, then automatically throughput will be less. So that we had discussed, and based on that particular thing, the evaluation of the things will be done, and we have seen that how a resource allocation will be done. The main constraint which we have seen is like that to improve the throughput, to improve the throughput we have to utilize the 100% of the bandwidth capacity and all. What we will tell the senders that sending the resources that you send a more packets. Once more packets will flow into the traffic or into the topology or a network, then automatically there will be a chances of a congestion. Once a congestion occurs, then automatically a delay will be increased. Now always throughput is proportionate with this particular delay. That means whenever the throughput will be keep on increasing and it will go one particular stage like this, and we have seen in a graph also, then automatically the throughput will come down as the delay will keep on increasing. So which is that particular point in evaluation stage? We have to observe which is that particular point where the throughput and the delay will be in a constraint. So that is a good performance based on that, where we can control the traffic, and these things will be done. How these things will be done? The another one important concept here in a resource allocation is on a queuing. So there are different types of queues will be there, and we'll see now how the different types of queues will work, and which queue is better than other queues, and how a queue limit will be maintained in a traffic at a routers, especially how a router will manage with that particular queues, and how a dynamic queues, that is active queue management, EQMs, will be done. So these things we are going to discuss in today's topic. Now I will share this particular PPT, and we'll proceed with that particular thing. Yeah, now coming to the queuing disciplines here. First, we'll go with the queuing discipline, that is the idea of FIFO queuing. First in and first out, which you have already studied in operating system and other many subjects. Also called here first come first served. In our networking languages, serving is very much important. So which is a first come packet and first served packet. So queuing is a simple, and it's a very simple technique, that is the which queue is coming and where. The first packet that arrives at a router is the first packet to be transmitted. Given that the amount of buffer space at each router is finite, if a packet arrives, you know that always the router, whatever router is there, the buffer will be in a finite stage, means some based on a problems, some amount of that particular buffer will be there in a router. If a packet arrives at the queue, means at a buffer space, once the buffer space is full, then the router discards the packet. For example, assume 50 packets capacity is there, and first packet will come, second, like that, all 50 packets will come. Still, first packet is not processed, just assume, and a 51st packet will come. There is no space to keep that in a queue. So what happens? Automatically, the router will discard that particular packet. Once bucket is full, automatically it will discard. That also we have studied. Now this done without regard to which flow the packet belongs to, or how important the packet is. In a FIFO method, it never thinks that how important of that particular packet and which flow, from which source this particular packet is coming. Without that particular regardness in a FIFO, whatever the packet, last packet is coming, if the capacity is full, it will delete that particular packet. This is sometimes called a tile drop. So in a lab program, we have used this drop tile. drop tile queue. We have used this drop tile queue in a first program and as well as in a second program. And we have seen how a drop tile queue will work here. Whatever a queue limit we have taken, for example, 20. So 20 bytes means that whatever 20 capacity of packets which we have taken. So if 20 packets apart from that packet is coming means it will be dropped at that particular tile. So this will be taken into the since packets that arrive at the tile end of the FIFO are dropped. So whichever a packet is coming at last at the tile, it will be keep on dropping at that particular stage. Note that the tile drop and the FIFO are two separate ideas. FIFO is a scheduling discipline which you have seen in OS. It determines the order in which packets are transmitted. Tile drop is a drop policy. It determines which packets get dropped. In a FIFO, we will observe that which packet will be processed, first packet. But in a tile drop, which is the last packet which has been came when queue is filled and which is a packet it has been dropped, that will be observed in a tile drop queues. Now how this you can see the differences here. The A figure will shows the FIFO means arriving packet is there here. Now free buffers is there here. The next buffer whatever is there, this is filled I think 3. Next to transmit is this one. Assume that this will be taken inside. Now assume the tile drop FIFO how it will works. Next to transmit is this. Assume the entire queue is filled here. This shows that figure entire queue is filled and arriving packet whatever is there at the tile it will be dropped now. Why? Because the queue is filled here. Now that is tile drop at a FIFO queue. So in this way the tile drop will be done at a FIFO queue. If space is there it will be taken inside. Now here no space is there. You can observe that the entire queue is filled and the next packet to be transmitted is here. It has been shown. And now entire queue is filled. Now at the meantime, if other packet is coming at the tile itself, that packet will be dropped. So that's why we'll call it as a drop tile queue, right? So here the packet will be dropped. Coming to the next thing. A simple variation on a basic FIFO queuing is a priority queuing. Now we'll step into the next queue format. So now here we'll change a simple change we are going to do in a FIFO. That we'll call it as a priority queuing. So what change we are going to do? I'll tell you now. The idea is to mark each packet with a priority. The mark would be carried, for example, in the IP header. Now what we are going to do, whatever in a packet header, we'll mark the priority of that particular packet. Means preference to that particular packet where a router will see based on a priority, it will give a chance. Highest priority which packets is there, for that the first chance will be given, the lower priority packets will be given aside. So even though they are coming, the lower priority packets, even though coming first, the higher priority packets will be given the preferences. The routers then implement multiple FIFO queues here. So this is very much important. Whenever the priority concept is there, it will be not in a single queue. So one for each priority class, a queue should be there. Always. For example, I will tell you, when you go to the any big temples like Tirupati, if you go there, you can see that there will be no single queue will be there. There will be different queues will be there based on different way of moving. The Dharma Darshana will be there as a free Darshana. So a queue will be a separate entry point will be there, and 300 rupees separate entry point will be there. Some VIPs separate entry point will be there, and some other sevas separate entry point will be there. Why this separate entry points, I'm telling, separate entry points, why it is needed means to distinguish the packets on their priorities. Who is a VIP here? To distinguish a VIP, a separate way to the VIP will give. Everyone will go and join at one particular place. That is different. But at an entry point, that is a differences will be there. So same thing here in a router, instead of maintaining one queue, one FIFO queue, the different FIFO queues will be there based on priority. Class 1, class 2, class 3, class 4 like that. that based on their priority classes, a different queues will be there, and the packet based on that priority, it will be taken into the queue, and process will be done based on a priority. The router always transmits packets out of the highest priority queue if that queue is non-empty before moving on to the next priority queue. For example, highest priority queue will be given the first preference, means that packet. If no packets are there, it will comes to the next priority. If no packets are, it will like that. It will comes to the low priority at last. Within each priority, packets are still managed in a FIFO manner only. Here, even though it's a priority is there, here also based on a priority, first in first out will be taken into the consideration. That will be noted here. So that is a priority queuing. Now fair queuing. What is this fair queuing? We'll see. The main problem with FIFO queuing is that it does not discriminate between different traffic sources, or it does not separate packets according to the flow to which they belong. So what is there here in a FIFO method, either it's a priority based or ordinary FIFO, what happens here, from which source the packet is coming and from which traffic source the packet is coming, that will not be taken into the consideration. It does not separate the packets according to the flow to which they belong. Now, fair queuing, what is this? This is an algorithm that has proposed to address this particular problem. How? So from which source it is coming and which traffic it is coming. So what is the benefit of that particular packet? Either that packet should be taken first and all based on a source and a traffic. So that the idea of the fair queue is to maintain a separate queue for each flow currently being handled by the router. Now, not based on a priority, based on a flows. How many flows are coming? How many senders are there? How many flows are coming? So based on a sources or a flows, the router will handle this particular queue. That is called as a fair queue. Now the router then services this queues in a sort of round robin method. What is this round robin method? How many flows are there? So you know that round robin method is source number 1, source number 2, source number 3, source number 4. Assume 4 sources are there. It will fix some quantum time. It will give a chance to first, second, third and fourth. Again first, second, third and fourth based on some quantum time. For example, assume that 5 seconds for each and every flow. So 5 seconds will be given to first flow, second flow 5 seconds, then 5 seconds, then again first flow 5 seconds. So in this way, in a fair queue, the queues will be maintained based on the flows. Now you can see here how fair queuing will be done. Now flow 1 is there, so these many packets are there. Based on a quantum time, it will fix flow 2, flow 3, flow 4. So again, round robin service means it will repeat based on a time. So again, it will comes to 1, 2, 3, 4. Again 1, 2, 3, 4. Like that, it will come. Now fair queuing, the main complication, what is there here? Means what is the constraint in a fair queue? With a fair queuing is that the packets being processed at a router are not necessarily the same length. So here that is the problem. So how the process will be done, it will be not in the same length. Assume that the flow 1 is coming from Ethernet, the flow 2 is coming from other network, that is Wi-Fi, flow 3 is coming from optical network, assume ringtone network. So where packet sizes will be different, right? But if you fix one quantum time for that, for some flows it will be very fast and some flows it will be very slow. Then how to do this particular thing? This is a problem here, right? In a fair queuing. To truly allocate the bandwidth of the outgoing link in a fair manner. That is how a fair manner. Now you have to decide that what type of flow it is. Means which type of network this particular packet is coming. So what is the size of that particular packet? Then based on that you allocate the sources. So then if you allocate the queue sources for that, then it is good. So how to do that? It is necessary to take a packet length into the consideration. So I am telling that you take a packet length. In a flow 1, what is the packet length? In a flow 2, what is the packet length? In a flow 3, what is the packet length? You have to take that particular thing into the consideration. Then you have to means you have to fix a time for that. Let it be round robin, not an issue. For example, flow 1, I will fix some 10 seconds. Flow 2 is Ethernet, a small packet is there. I'll fix 5 seconds for that. Then again it will repeat. Then okay, somewhat means truly if you take then some fairness will be there. For example, if a router is managing two flows, assume one with packet size of 1000 bytes and other with a packet size of 500 bytes. Perhaps because of fragmentation upstream from this router, okay, then a simple round robin servicing of a packets from each flow's queue will give the first flow 2/3 of the link's bandwidth and the second flow only 1/3 of its bandwidth. So this is okay here. See what I am telling you, if 1000 bytes of packets is there and 500 bytes of packet is there, round robin servicing will be there, right? But here observe here, the fixation of a bandwidth, observe here, 2/3 will make a 3 parts of that entire bandwidth. 2 parts will be given to the 1000 bytes packets and 1 part will be given to the 500 byte packets. It's a fair enough. Why? Because almost on 50% size of a packet is less. So then here somewhat okay. Now coming to what we really want is bit by bit in a round robin. That is, the router transmits a bit from flow 1, then a bit from flow 2 and so on. Clearly it is not feasible to interleave the bits from the different packets. Now again, what happens, a problem here, constraint here, it is not feasible to interleave, means you can't leave the bits of a packet. Okay, I fixed the bandwidth, so here the bits transmission will become a problem. Now in a fair queuing mechanism, therefore simulates this behavior by first determining when a given packet would finish begin transmit if it were being sent using bit by bit round robin, and then using this finishing time to sequence the packets for a transmission. Then what we are going to do to solve that particular problem, now bit by bit, if it has to solve that particular problem, we will fix some time. So what is that particular finish time is there? Based on that bandwidth is allocated now. We'll fix some time also. Within this particular time, these many bits will go. So that assume that will be of one packet or half packet it will be there. So these many bits within this particular time has to be moved. So if you keep like that, then somewhat the fairness will be there. Now again in a fair queuing, to understand the algorithm for approximating bit by bit round robin, so how we can approximate the algorithm, how we can fix a time. Consider the behavior of a single flow first. For this flow, let Pi denote the length of a packet, Si the time when the router starts to transmit the packet, I then time when router finishes transmitting the packet, that will be a Fi, Si and Fi. Clearly Fi, that is the router finishes the transmitting of a packet, will be equal to the start time, that is Si plus length of the packet, bit by bit if you take length of the packet, that is Pi. So that will be clearly taken into the consideration, Fi. Now assume when do we start transmitting packet depends on whether the packet I arrived before or after the router finishes the transmitting packet I minus 1 for the flow. That means before flow it has been completed, then it will comes to I. We know that means flow wise it will come. Let AI denote the time that the packet I arrives at the router. Let it be AI, that coming time. Then Si is equal to maximum time. So Fi minus 1, that is the finish time of previous flow, correct? And what is the start time, means what AI it's now started, that will become a start time. Assume that I'll start with 0 second. Previous flow has taken some 10 seconds. Now again next flow has to start. When it should start at 11th second. So 10th second it has finished, correct? Are you getting my point? And this is a 11th second. So Si should start from max of 11th second, correct? So Si is a now 11th second. Now where is the finish second? Observe carefully. The maximum of fi minus I, this one means SI here, what we have taken 11th second plus packet size. What is the packet size? Assume 1 second for 1 byte, just for a sake I am telling. So then assume that some 1000 bytes are there, 1000 seconds it will take. 11 plus 1000. So 11 plus 1000 if you take into the consideration, so that will be taken as here. So how we have taken that 1011 will be taken into the consideration. That is the finish time. Next, fair queue. Now for every flow we calculate Fi, means finish function, for each packet that arrives using our formula. When then treat all the Fi's as timestamps. Now I came to know that for first flow what is the finish time, and for second flow what is the finish time, like that. Now for each and every flows finish time I know that, timestamps I know, we know that. Next packet to transmit is always the packet that has the lowest timestamp. So which is having a lowest timestamp, so that finished packet will be taken into the consider the packet that should finish transmission before all others. Now you can see here how this can be done based on a fair queuing. Example of fair queuing in action A. Packets with earlier finishing times, you can see A. This is a packet with us earlier finishing times, FA, and 10 will be taken next. So first these two and then flow 2 will be taken. Now sending a packet already in a process is completed. Now flow 1 is arriving, flow 2 is there already. Now already it has been sent. Next flow 2 will come. Right? So in this way it will be sent. Now TCP congestion control algorithms. What is this TCP congestion control algorithms, and how this TCP congestion control algorithms will work? We'll see now in this particular topic. You know what is a congestion first. The congestion is a one where if the flow of the packets are more and the queue capacity has been filled at a router, then automatically the coming packets will be discarded, means it will be dropped. That situation will call in a network topology as a congestion at that particular router. Now TCP congestion is very much important. What do you mean by TCP congestion? If congestion occurs, how a TCP congestion control will be done? That means how your TCP will make your senders and sources to control the flow, where automatically a congestion will be released at a router. How your router will intimate that your senders or sources that your traffic jam has been occurred. So these TCP algorithms are there here to do some congestion controls. Means the congestion shouldn't be done there. If congestion occurred, then suddenly the way of sending packets from a TCP window will be changed at a sender size. Then automatically it may reduce. So automatically the traffic will come down. Then automatically the trust load on that particular router will come down. So TCP congestion control was introduced into the internet in the late 1980s, not so far. So that is Jacobson, he has introduced that. Roughly 8 years after the TCP IP protocol stack had become operational. Already internet is there and TCP IP packet protocol stack is there, suite is there. After 10 years of that, the congestion control in a TCP concept came out. Now immediately preceding this time, the internet was suffering from a congestion collapse. At that particular 10 years, there was a huge congestion collapses is there in the internet. Hosts would send their packets into the internet as fast as the advertised window would allow. Congestion would occur at some router, same what I told you, causing packets to be dropped, and the host would time out and retransmit their packets, resulting in even more congestion. Same thing. There it will come, the packet will drop, and again retransmission of packets will be done, again it will drop, again retransmission of packets will be done, resulting in a more congestion will be occurred there. The idea of TCP congestion control is for each source to determine how much capacity is available in a network, so that it knows how many packets it can safely have in transmit. Very simple. Now, if TCP congestion means if sources of a TCP will comes to know that what is the situation of a traffic in a network, then based on the situation of a traffic in a network, it can transmit the packets into the network. Then congestion control will be done, no congestion will occurs. If it comes to know that, how it will come to know that, that is the important question here. Once a given source has this many packets is transmitted, it uses the arrival of an acknowledgement as a signal that one of its packets has left the network, and that it is therefore safe to insert a new packet into the network without adding to the level of congestion. So once a given source has these many packets, means some window of a packets, capacity of a packets, it has been sent. So it uses until the acknowledgement has to come. We know that we have studied in a sliding window protocol as a signal that so it can resend the, means it can leave the packets to the network. Now, what is the safe? Assume that now it's still your acknowledgement is coming and you have released the packets, inserted a new packets into the queue where adding of a level of congestion will become more. By using acknowledgement packets to face the transmission of packets, TCP is said to be self-clocking. So always TCP in a self-clocking. What is that? If packet reaches there, acknowledgement comes, then based on acknowledgements, it will send a packets, new packets or retransmission of a packets. It will decide based on that particular acknowledgements. Now, additive increase, multiplicative decrease. We'll see how this algorithms will work in a TCP. Now, these are the very important algorithms which you have to take in a TCP protocol. Means your TCP protocol has been built, coded based on this particular algorithms. Additive increase first. TCP maintains a new state variable for each connection. We'll call that as a congestion window. Means each source will have this particular window. Whatever a window of packets it's sending, we'll call that as a congestion window, which is used by the source to limit how much data it is allowed to have in transit at a given time. So at one particular time, how many packets it can send will be based on that particular congestion window. The congestion window is congestion controls counterpart to flow controls advertised window. Now, based on this particular means your congestion window, whatever is there, that is the one which is a counterpart for a controlling of a congestion. Why? Because based on a congestion, this particular control will be there on a packets to be sent. So as well as the flow control will also be done based on a advertised window. TCP is modified such that the maximum number of bytes of unacknowledged data allowed is now the minimum of the congestion window and the advertised window. Now, whatever unacknowledged acknowledgement not came, but the packets has to be sent in a queue. So how many packets you have to send to fill up your bandwidth? So that will be based on the congestion, which means the load on the network, as well as the advertised window. Means your receiver is advertising you send only these many packets where I can hold. Based on these two variables, your congestion window will be depending. Now, additive increase, multiplicative decrease. You see this. TCP's effective window is revised as follows. Max window always, observe here, max window always will be equal to minimum of congestion window, comma, advertised window. Whichever is minimum, that we are going to take into the consideration. Right? Now, effective window is equal to maximum window minus last byte sent minus of last byte acknowledged. Assume last byte acknowledged is 1. Last byte it has been sent. In between whatever is there, that will be there in a queue. So max window it can send is, so based on that part. So maximum window is there here. Max window, what it can send more, minus of that remaining bytes it will take. That is, max window replaces the advertised window in the calculation of effective window. Thus, a TCP source is allowed to send no faster than the slowest component the network or the destination host can accommodate. Whatever your network takes the load, based on that, and as well as your receiver will takes the load, based on that your TCP source allowed to send the packets. Why? Because you are taking both the variables into the consideration, that is congestion window and advertised window. Now, coming to the next, the problem of course is how the TCP comes to learn an appropriate value for a congestion window. Now, how to define a congestion window? That is the problem. You know that advertisement window will be given by a receiver. Now, how a congestion window can be fixed, where you can take a maximum window into the consideration. So unlike the advertised window which is sent by the receiving side, as I told you, of the connection, there is no one to send a suitable congestion window to the sending side of the TCP. If no one is there to tell how much your congestion window should be there. So how to do this? The answer is that the TCP source gets the congestion window based on a level of a congestion it perceives to exist in the network. Now, what is the congestion level in your network? What is the traffic level in your network? Sorry, based on that your congestion window will be there. Then how the source will comes to know that what is the load and what is the traffic in a network, correct? So how it will comes to know that? This involves the decreasing the congestion window when the level of congestion goes up and increasing the congestion window when the level of congestion comes down. Taken together, the mechanism is commonly called additive increase, multiplicative decrease. Both things you have to take. Now I will tell you. What is additive increase? I will tell you very clearly. The congestion window will be there. It will be 0. It will start. It will send a packet 1. It will send next to 2. It will send 4. Still no congestion is there. It will send 8. No congestion is there. 16 packets at a time will be sent. No congestion is there. Are you getting? No congestion is there. Then what happens? It will send again 32 packets at a time. Assume congestion will occur at a router. Now router will send a congestion message to the source. Then automatically the source, what it will do, it will go to the, it will change the algorithm to, from additive increase, it will change the algorithm to multiplicative decrease. That means it will cut down to the window size to half of it. Whatever 32 is there, so it will cut down to the 16. Assume still congestion is there, again it will cut down to 8, again it will cut down to 4, again it will cut down to 2, then 0. Like that, this is a multiplicative decrease which will be come down, and additive increase, it will be increase in an exponential manner. So both the things will work in this particular method. Now additive increase, multiplicative decrease, the key question when this is, how does the source determine that the network is congested and that it should decrease the congestion window? When it should do that? The answer is based on the observation that the main reason packets are not delivered and the timeout results is that a packet was dropped due to the congestion. It is rare that a packet is dropped because of an error during transmission. So because of error, packet dropping is rare. So due to congestion only, packet drop will be more always. Therefore, TCP interprets timeouts as a sign of congestion and reduces the rate at which it transmits. How it will decrease, I am telling you. So automatically, so the timeout time will become more, then automatically the TCP window will be reduced. Specifically, each time a timeout occurs, the source sets a congestion window to half of its previous value. Underline this, I have told already. Half of its previous value. That is 32 is there, it will cut to 16. 16 is there, it will cut to 8, like that. This halving of a congestion window for which timeout corresponds to the multiplicative decrease. Additive increase means exponential increase. Multiplicative decrease means half of it will decrease, like that. How beautiful the algorithm is, you can see now. In this way, the congestion window will be maintained. Coming to the next thing. Although congestion window is defined in terms of bytes, it is easiest to understand the multiplicative decrease if we think in terms of whole packets. For example, suppose the congestion window is currently set to 16 packets. If a loss is detected, congestion window is set to 8, half of it. We know. Additional losses cause congestion window to be reduced to 4. Then still congestion is there. Then 2 and finally to 1. Congestion window is not allowed to fall below the size of single packet. Means it never comes down to a less than a single packet, or in TCP terminology, the maximum segment size, that is MMS, that you have to make a note. Then coming to the next, the congestion control strategy that allows the so now no, you shouldn't be at always 8. Now you have to increase. Why? To utilize the bandwidth correctly. Now every